Hello, welcome back. In this video, we're going to look at some practical linear accelerator systems for medicine and that are on offer by some of the vendors currently, and go into some of the practical aspects of that. If you haven't watched the videos before up to this point, please go and do that. We talked about the fundamentals of linear accelerator beam production, the collimation system, and so on. So it helps to know that as we go into this practical discussion. I'm sort of two minds about this. Normally, if I give a talk or teach, I don't really like to talk about specific vendor products because it sounds a little bit biased, but I want to keep this very practical, kind of concrete things that you see in clinical operations. So I'm going to go into some of these in this video. I'm not endorsing any product or anything like that. And I will actually leave out quite a few products that are out there. I'm just not going to have time to mention everything. So please take that in mind as you watch this. And I hope it's helpful from a practical point of view. So here we go. So I'm going to start by talking about linacs systems that are in a C-arm configuration. You've seen one like this already in the previous video, so this should be somewhat familiar. The systems are quite advanced. The gantry rotates around, as we saw last time. This system you're seeing here is imaging, right in imaging mode right now. This is the imaging system taking a CT image that can provide very precise alignment. So it's very advanced, but let's look back a bit at the history of this. So here is a cobalt-60 teletherapy unit. So you've learned about cobalt-60 in the previous videos, so you can appreciate how this works. It's got a very high strength cobalt-60 source in the head that opens for treatment. This was really an outgrowth of World War II when nuclear reactors were developed, and it was discovered that you could activate cobalt-60 to very high specific activities that could be used for therapy. The first units were developed in the 1950s. A pioneer of this was Harold Johns at University of Saskatchewan, and there was also a unit built at University of Western Ontario at about the same time, and they treated their first patient in October of 1951. And these cobalt teletherapy units remained a workhorse for radiotherapy for 20 years until the 1970s, when they became gradually replaced by linear accelerators, at least in North America and Western Europe. So linear accelerator technology is quite a bit more complex than a simple cobalt source, as you'll appreciate from the previous videos, but the investment and development was thought to be justified. So let's stick with the history for a moment. So we come to August 19th, 1953. That was the first treatment of a patient with a linear accelerator. That happened London Hammersmith Hospital, and this was a 8 MV linac developed by a company that is no longer manufacturing these units. Around the same time, there was also development going on in California. That work was pioneered by Dr. Henry Kaplan, an oncologist who worked with physicists there to develop linear accelerator technologies like we've learned about. And here was Dr. Kaplan's first patient, Gordon Isaacs, is a 2-year-old boy at the time, treated in 1957 for a retinoblastoma tumor. And he lived for many years after this. Dr. Kaplan went on to do pioneering work in RT treatments for Hodgkin's lymphoma, as you probably know. And the technology continued to develop at the same time. In 1968, Varian released the Clinac 4, which was a C-arm linac-based unit. It wasn't the first isocentric unit. There was one in the 1950s in Newcastle and others, but this is the one that really became the workhorse for radiotherapy and established this type of engineering solution as the dominant one for many years. And of course, these units have advanced, and now there are many options and many kind of bells and whistles, you could say, that help guide treatment and make it more accurate. So I'd like to step away now from the C-arm linac units and talk about some of the other solutions, because there are others. Here are two type of systems out there, and I'm going to go through each of these in a little bit of detail to show you the type of engineering that is behind these linac-based systems. So now I'll talk about the tomotherapy system, which is a trade name of a system made by Accuray Incorporated. As you see, it looks a lot like a CT scanner, although on the inside it's different, as I'll explain. But basically the patient gets on the couch and there's a continuous motion of the patient through the bore and as the treatment progresses, so that you can treat a field up to 135 centimeters long. There's no oblique angles that you can do. In other words, like I showed with the C-arm, you could come in at different angles by angling the table and the gantry. In this case, it's all just one straight coplanar field. So the gantry rotates as the couch moves in, and here's the equipment inside. Let's pause and take a look at this. So you've got a linac here. You'll note it's really small. It's a very small linac. There's the jaws and the collimators. I'll explain in a minute. Down here there's a detector that allows for imaging. And then finally there's a beam stop down here that stops the beam, which reduces the shielding requirements in the room. So one thing to note about the tomotherapy system is that the beam does not use a flattening filter in it. So you'll recall from previous videos that the standard linac system has a flattening filter here, and the purpose of that is to make the beam profile flat. Tomotherapy doesn't use that filter. It just has a beam that's unflattened. That's called a flattening filter free beam, FFF beam. And it was one of the first such systems to use such a beam. So here's another look at this same unit diagram. And you'll see it's an 85 SAD machine. That helps with the output. Also the bore size is 85. Now let's look in at the jaw and the MLC and understand that. Here's a movie that shows during treatment the MLC opening and closing. Let me stop this for a minute and explain it. So first of all, you'll see the jaws on either side here. That controls the width of the slice that you're irradiating at any given time. That width being in the sup-inf direction in the patient. Those jaws can be set for a width of either 1 centimeter, 2.5, or 5 centimeters. And then in the newer unit, they can be controlled dynamically. And then inside those jaws are the leaves. So these are 10 centimeter thick tungsten leaves, and they're controlled pneumatically with very fast air-driven motion, which you saw in the video. So they go very quickly. Right now you'll see a field where there are two segments open, irradiating two strips in the patient. As the unit rotates around, those strips move around and you build up a dose distribution. So here's what it looks like dynamically then. So as I mentioned, you can do imaging with the detector system down here. That's done in a CT mode. As the unit spins around, you acquire images in that detector, and then those are reconstructed. You can do a match between the reference scan and the scan on treatment, as seen here. Now, the first use of tomotherapy on human patients was in 2002. At that time, it was one of the first units to offer image guidance during treatment, and as such, it really pushed the field forward in that direction. So this is the essentials of tomotherapy device, and there's an APM report that describes this device a little more and the QA issues around it, although the report is now a bit dated. So now I'm going to move on and talk about the CyberKnife system, which is also manufactured by Accuray. There's an APM report about this, TG135. It's a bit outdated now, like all these reports. Unfortunately, the technology moves very quickly, faster than reports can be generated. The main component of this is a linear accelerator in the X band, and you see the beam come down here. It's very compact, so it can be put on this manipulator arm that can move it around in 6 degrees of freedom and point in different directions. So it's a non-isocentric system. Here's the table, exchange table of different collimator sizes that a robot can pick up. Patient sits here on the couch. And then it's got an imaging system. So there are two tubes, X-ray tubes, up in the ceiling here and here. And a beam comes down from the tube and is imaged by panels in the floor. And so you get two images, one here and one on the other side. And that can give you a stereoscopic localization. So you imagine if you have a point, if you have image of it from two angles, you know where that point is in three-dimensional space. So that's how that works. So it's very good for bony anatomy and other fiducials and so on that can be visualized on planar radiographs. So let's look at the beam collimation system for a minute. This is the original design. These were circular collimators that can be placed into the head under the linac. There are 12 of them, ranging anywhere in size from 5 millimeters up to 60 millimeters. The unit developed over the time since it was first cleared by the FDA in 1999. The second type of collimation system that came out was the Iris. This was a bank of 6 tungsten blades that could be opened and closed, kind of like a camera shutter. And then the newest system is shown here. This is the MLC-based system, and it allows for more control over the shaping of the beam, and it allows for larger field sizes up to 10 centimeters by 11 centimeters. So here we see this thing in action. You see the head coming down, and it's going to treat at the angle that you program it to. This is actually operating in probably like the most advanced mode. You can actually see the thing syncing with the respiration of the patient here. It develops a model based on imaging to a model of the respiration. But there are other things you can track as well, bony markers and so on, not necessarily in real time, but maybe an image every second or so, and then you image treat, and so on. They're treating from different directions, which in CyberKnife are called nodes, that kind of form a sort of a sphere around the patient. But this is not an isocentric treatment, usually. So those are the basics of the CyberKnife system. I'd like to wrap up this video by talking about MR-guided radiotherapy. This is enabled by new technology in which the linear accelerator is combined with an MR scanner. Here's one of the systems. There's 2 vendor systems out right now. Inside is an MR and a linac. The MR allows you to visualize soft tissue. Here's an example study from Carrie Glidehurst's group, one of the pioneers in this area. And you can visualize the liver here, you'll see, and soft tissue. And you can also watch motion during treatment. Here you can see the liver moving down and then up. Here I'm showing the inside from the unit of one of the vendors. And if you look closely here, you'll see our old friends, the klystron, the circulator, and the waveguide all lined up around the edge. And this whole ring goes in between 2 poles of the magnet on the left and the right, and that provides the ability to image and the treatment on the same unit. As you can imagine, there are some significant engineering challenges that goes with operating a linac in the presence of a magnetic field, but that's been largely solved. So this is meant as a short introduction of this technology, and we're going to come back to this in video 21.1 after you understand imaging a little better. I hope this served as a practical resource for some of the systems that are currently out there. Sorry I couldn't mention all of the systems out there. You're going to see some of these technologies come back again in video number 22 and on, when we're going to talk about image guidance systems. And I'm going to come back and look at some of the image guidance components of the systems that I showed you in a little bit more detail. For now, we'll leave it there, and we'll see you in the next video. Thank you.